Hey all dear students, let's see this question of Irodov from Electrodynamics. It's a question of plotting the electric line of forces. We'll go ahead and also plot the corresponding equipotential surface. So the question asked, determine the electric field strength vector if the potential of this field depends on the xy coordinates, as in case A, phi is equal to ax square minus y square, and case B, phi is equal to axy, where A is a constant. Draw the approximate shape of these fields using line of forces in the xy plane. So this is the potential as a function of x and y. I can directly plot field lines using the potential, but it is also asked to find the field strength, and that will be kind of a cross-checking for me to if I use the field strength vector expression also. So the x component of the electric field would be minus del phi by del x, and that would be nothing but minus 2ax. And similarly, the y component of the electric field in this case would be minus del phi by del y, and that would be a 2ay. So clubbing these two, x component and y component, I'll get the finally electric field vector as a ex I cap plus ex j cap. So I can take a 2a common, so minus x I cap plus y j cap, and it is what the electric field in case 1. Now in case 2, the potential is a x y. So x component of electric field is minus del phi by del x, and that would be minus ay, and y component of the electric field would be minus del phi by del y, and that will be minus ax. So again clubbing these fields together to get the final electric field vector ex I cap plus ey j cap, that would be, I can take a minus a common, and it is a y I cap plus x j cap. And now let's go ahead to plot this field line, the potential field and also the electric field. So let's start with the case A. So in case A, the expression of the potential is a x square minus y square, and expression for the electric field strength vector is 2a minus x I cap plus y j cap. I'll start with plotting the equipotential surface. So equipotential surface is a surface at which at all the points the potential is same. So for the EPS, the condition is phi is equal to constant, and A is a constant. So phi is equal to constant would mean x square minus y square is equal to constant, and one constant, if I choose a different constant for this expression, I will get different EPS. So let me plot an EPS which has a zero potential. If x square minus y square is 0, x square minus y square is 0, so phi is 0 means that is a zero potential. So obviously clear that if the x square minus y square is 0, the solution would be y is equal to plus minus x. So that will be that EPS. So that EPS would be like this. So I can plot that EPS. This is the xy plane coordinate axis. So just let me plot carefully. This is y is equal to x line, like this. On this line, I am writing the potential value of potential on a box. So here potential is 0, and once again phi is equal to 0 means x square minus y square is 0, that means y is equal to plus minus x. So y is equal to minus x is also an EPS of 0 potential. So this is a this. So this is also a 0 potential EPS. And now if I take any other value of phi, non-zero, so in that case x square minus y square is a some constant, and the constant that thing is a basically hyperbola. So let's go to a a graphing tool and just I'll put the different value of that constant and see how the hyperbola looks like. So this is a graphing tool. I'll take different values of x square and minus y square and see how it looks like. Basically, it's going to be a hyperbola. So let me choose first x square minus y square is equal to 1. So this is a hyperbola, and basically y is equal to plus minus x are the two asymptotes. If I take another value, x square minus y square is equal to say now 10. So this is this hyperbola. So as I will increase potential, positive potential, so hyperbola will shift like this, will shift something like this there, that here it will shift like that. I can choose one more hyperbola, x square minus y square is equal to say now I can take 20. So that is this hyperbola. So you can see that x square minus y square is equal to 0 was a hyperbola of 0 potential, and as I am increasing x square minus y square, the potential is increasing and it is shifting towards this. In the same way, if I take a negative potential, the hyperbola will be on this region like this, like this, like that. So I can choose x square minus where's y, this y square is equal to say minus 1. So this is this hyperbola and another branch of this hyperbola. So same way, if I increase the potential in negative, we will get the hyperbola along this like that. So I can take one more, x square minus, where is that, y square is equal to say minus 10. So we'll get this hyperbola, so as expected. So now we can go and plot the EPS. So I'll start with the let me assume that this A is positive. So for the positive potential, I can choose some EPS which has a positive potential, say potential 10 volt. So that EPS would be something like this. That EPS would be something like this, and its potential is say 10 volt. Another branch of this EPS would be like this. This is say 10 volt potential. If I plot a EPS with a minus 10 volt, so the same way that will be something like this, that will go with a negative potential like that. But it's not very clear. So EPS of negative potential just shown, that would be like this. Suppose this is an EPS of potential minus 10 volt. Another branch will go from like that. Minus 10. I can increase in the positive, say that I can take the EPS of 20 volts, so that would be like that. Same way here. And in the negative potential, negative potential EPS, like that, like that. So these are the EPS. EPS means equipotential, and we know that the electric line of forces are perpendicular to EPS. So I can plot using this EPS the electric line of forces. So I can start drawing the ELOF, electric line of forces, say from here. So a line that is perpendicular to EPS, so that would be the approximate shape would be something like this. This is going to electric line of field. This is going to electric line of field here. Here, purple color are the electric line of forces, like this, and here that is going to be like this, and like this. Here it is going to be like this and like this. And now I have to show the arrow. See, we know that the electric field decreases in the potential decreases in the direction of electric field. So here see, this is a higher potential, this is lower potential, this is 20, 10, 0, minus 10, minus 20. So potential is decreasing in this direction. So the lines of electric field would be along this direction. So here the electric field line would be like that, here also. In the same way also. Here this is a 20 volt potential, 10, 0, minus 10, minus 20. So line of electric field would be like that here also. The same logic I can apply here. So this is 20, 10, 0, minus 10, minus 20. So the lines would be here like that, and the same would be like that. And let me cross check this. E is equal to, I plotted this assuming A to be positive. So here 2A, let's, for the sake of simplicity, let's take 2A is equal to 1. So E is a minus xi cap plus yj cap. Suppose I take this point. I take this point coordinate is 2, 0, 2, 2. So at 2, 2, electric field would be minus 2 I cap plus 2 j cap. And that would be, this is the x component, this is the y component. So electric field tangent would be like this, and isn't it looking like that? So the tangent here is along this direction, that is like that. The same way you can check all other points. So basically we have now plotted the dark red lines are the equipotential surface, and the purple lines are the electric line of forces. Now the second case, the phi was AXY. So here phi is equal to, in case B, phi is equal to AXY, and its corresponding electric field was, we got minus A yi cap plus xj cap. You will see that basically these two cases, in the case 1 and case 2, the EPS and ELF will get exchanged. So let me start plotting this EPS. So for the EPS, phi is constant, mean xy is a constant. I'm assuming A to be a positive constant. For the sake of simplicity, you can assume A to be 1. So basically phi is equal to xy. So different value of xy, product of xy will give the different potential. So first of all, let's take the zero potential. If either x or y is 0, so this potential would be 0. So on the coordinate axis, x-axis y is equal to 0, on the y-axis x equal to 0. So this is the an EPS of potential 0. So this is a 0 potential EPS, and this is also 0 potential EPS. And then xy is equal to constant. If I plot y versus x for xy is equal to constant, that would be rectangular hyperbola. So if it is a positive constant, so the graph would lie in the first and the third quadrant like that. So if I take some positive potential, so the graph would be like this and like this. This is for a positive potential. So say this is for positive potential, say for positive potential 10. This is for positive potential 10. If I increase the potential, suppose this 20. So product of xy increase, the graph would be like this. This is a positive potential, say 20. And now if the product of x and y is negative, so the rectangular hyperbola will lie in the second and the fourth quadrant like that. So this is for, say, negative potential. The graph would be like this. The graph would be like this. Symmetrically I'm plotting. So suppose this is for the potential minus 10, and this is a minus 20. This is minus 10, minus 10 volt, this is minus 20 volt. And now once again we can plot the electric line of forces. They would be perpendicular to these EPS. So then start the plotting the EPS, electric line of forces. Suppose I start plotting from here. So one line would obviously be like this. One more important thing is that here the two EPS intersect. Where the two EPS intersect, the electric field has to be 0. And you can see that at the origin electric field is 0. So I'll not going to plot the electric field on these lines, but here other part, here the electric field will be along this, here electric field will be along this, and but at this point electric field is 0. So for the other points, the electric field line would be like this. Here the electric field line, keeping the fact that it will always be perpendicular to EPS. So the electric field lines would be like that here. Electric field line will be like this here, like this here. On this part it would be like this. On this part will be like this. In the same way here, like this. So once again these purple color lines are the electric line of forces, and we can now give their direction. See, start from here. This is a positive potential. Here and positive potential increases. So as I go from here to here, potential decreases. So electric field is in the direction where the potential decreases, or we can say that in the direction of electric field, potential decreases. So the direction of field line here would be like this, and the same way here it will be like this, like this, and you can continue here. Here also you can continue. Here we can make like that, and here we can make like that. So we have drawn the EPS and ELF, and you can again cross check. Suppose I can take once again say this point. This is a 2, 0. So at 2, 2, at 2, 2, taking A is equal to 1. So this E, I've already drawn these diagram assuming A to be positive. So taking A is equal to 1 for the sake of simplicity, that would be the minus I cap minus J cap. So actually I could have taken here somewhere, but okay, you can give that. So the lines would be something like that. So you can see that here the line is, the tangent to the line is along that is along this direction. So we have drawn the EPS and ELF. Hope you enjoy this video. Stay tuned for the next video. Thank you.